Right, so welcome to this one. I'm going to show you how to emulate an I2C device using ESP-IDF, or just the general architecture of emulating an I2C device for situations where you have the firmware but you don't have the hardware that uses I2C for communication. So let's say you have a new sensor you're trying to use, or a new, let's say, um, component you're trying to use in your design, but you don't have the hardware itself. But you need to test whether your I2C drivers work as expected. So emulation is basically just using a different hardware to mimic the intended functionality, which is I2C in our case. So in this short video, I'm going to show you how to set up two ESPs, one as a master, the other one as a slave, and communicate between the two. So it's a pretty basic thing. If you're used to, yes, if you know ESP-IDF, you know it has layers of uh, uh, design structures, and that won't be the focus of this one. So if an area is not clear in terms of ESP-IDF, it doesn't matter. You can actually just research on it, but my focus will be on how the emulation itself works. So right here I have two open projects, which is one is a master emulator, the other one is a slave emulator. So I'll start with the master and open its main file, main.c file, and clearly, or rather, the first thing that you notice is these two header files that are included uh, at the top here. That's a driver I2C header library and I2C master header library. So ESP-IDF has a master.h and a slave.h library, files, depending on what you're going to use. And next you have some utility files like error handling, and we are going to use a few RTOS functions and port macro utility for port definitions, especially for RTOS. So now, since this is a master, we know that I2C basically has one master and up to around 127 slaves, and each of these slaves has to have its own address for communication. So in this emulation, the first thing that we do is define the master, right? Rather build the master. So you can see before I explain that, there is the master, there is the slave, and then there is the bus on which this communication takes place. So this right here, I2C bus handle, is what is used to handle, or rather is a handle to an I2C master bus. Yeah. The next thing is we configure, or rather the first thing is we configure a master I2C bus. Basically, an I2C bus has several, or rather a couple of configurations that we need. So for the ESP I'm using, the first pin that we need is the SCL pin, right? The second is the SDA. So I've defined mine as 22 and 21, and then a couple of other useful uh, functions, rather variables, but these are default, so you can ignore this for now. Clock source, the default clock source from the from the ESP chip. And then this is the I2C port. Basically, an ESP has two I2C ports. That's num0 and num1. So you have to tell the master bus which port you're using. So after you configure this, you can see that this is abstract, right? Abstract. You initialize the bus using this function called the new master bus. And after that, what you do, you pass the reference to this struct, right? And you tell it to which bus are you feeding it to. So if you remember, you can see this I2C bus handle right here, and that's what we pass. So those two things will create a new bus. So it's like saying take this configuration and assign them to this bus. right? So from there we check the error. If there's no error, then we are good to go. Now the next thing is, now this bus will require us to use to have devices, or rather slave devices, on the bus itself, right? So the slave is called an I2C device. Most of these are, just to say that most of these structure names and type defs are available on the ESP-IDF documentation page, and actually are available on the ESP-IDF documentation, and they are pretty. The APIs are pretty well documented. So and there are a couple of examples right there to help you get started. So I2C device is basically an I2C slave, right? I2C slave. So I will mimic a slave that has an address 0x48, right? So the first thing that you realize here is the device address, which is basically the slave address 0x48. The next thing is what's the length of the address. You can have 10-bit addresses or 7-bit addresses. So I'm using an I2C address, which is 7-bit. And standard speed, what speed of communication are you using to communicate with your um, I2C device, right? So for standard speeds, we have around 100 kilohertz, right? This is right here, 100 kilohertz. It's not very fast, but it's not slow enough. It will be good for our use. This is I2C, so it's kind of half duplex, right? So again, this is a configuration variable. It's abstract, right? It is abstract. After that, we need to initialize or to add this device to the I2C bus to let the bus know that now we have a new slave device, right? Now, how we do that, again, there's a function that is called I2C master bus add device, and you pass the handle to the bus, the device configuration, which is just basically what you have defined here, the address, speed, and the address length, and then you pass the slave device handle. Basically, the slave device handle is nothing but a device handle type for the master to associate that slave on its bus, right? But it's not there's no configuration for this. It's just a handle that is passed. Okay, so again we check the error. If there's no error, we're good to go. So at this point we have the bus, we have a master, we have a device that has been configured and added the master. So what do we do now from there? Now for in our main loop, or rather in our super loop right here, we need to be constantly checking, or rather reading from the I2C device and check, is there data on this I2C from this I2C slave? Is there data from this I2C slave after every specific interval, or depending on how you design your application. So for me, I have put a 1000 blocking. This is actually, let me just say, this is a blocking delay. In actual production firmware, you wouldn't do this, but this was a test, so it doesn't really hurt it. You didn't introduce a blocking delay for anything actually. All right, so after delaying, or rather after every delay, we can, the next thing is we have this, I have this register global variable that stores the address of the data that is to be fetched. I'll explain that later in the I2C slave. So the next thing is we read data from the slave device by using this API function called the I2C master transmit receive. So what do we transmit, or rather what are the variables to this function? The first thing is the slave device handle. Which slave do we want to read from? And then after we read that data, where are we saving it to? So we pass a reference to the register right here, right? We pass a reference to the register. The next thing we do is the length of the data. No, sorry, we pass a reference to this register. Is like which register are we reading from the I2C device, because the I2C slave device can have it has different registers that hold different information. So if it is temperature and pressure and humidity and what that, all that data is placed in specific either sequential address registers, or basically the manufacturer will expose register addresses for you to read. So this is the register that I'm using, and I don't think I've defined it. Data address is defined here. Data address is right here, right? So based on my slave emulation, as I will show you, this address 00 holds the slave ID. Yeah, it holds the slave ID. Next, we want to read one length of data, and then we want to put that whatever we have read into this variable called data. Data is basically a uint8. It's right here. It's a 1 byte array, right? Okay, and the other variables follow. So we check for any error. If there's no error, we are good to go. After that, at this point, we would have received the data, so we just debug it, we print it to screen, and that's all about the master emulation. Now next is the slave. What does the slave do? Slave must wait for the master to, not really wait, but must always check if it's being addressed on the bus. If it's being addressed, it's a very simple thing. Check whether you're being addressed. If you're being addressed, check which register is being requested for. After you do that, dump that data into your buffer and then send it to the I2C bus. That's all. So this is the I2C slave code, or rather main file. So we have a couple of includes here, but at this point we including a slave.h, right? On the master we were including the I2C master.h. What else? Task handle. So the structure of this I2C slave is, there are two things. There's the receiving and there's the transmitting, because the master can write to us data. Of course they will write to us data, for example the address, and then we should receive, and then we should transmit whatever the master is requesting for. Okay, so from the top we have what is our slave address. We have 2 pins. Now this is not necessary unless you are emulating, because I am using an ESP32 to emulate. I need to, the I2C SDA and SCL need to be connected on the same lines, right? So I need to define, this is only for emulation, right? So I need to define which pin and SDA pin and SCL pin is being used for I2C for my ESP device. If you have a sensor, the sensor does not care about these 2 pins, because you can't define the pins. They'll just be automatic from your main slave file. Okay, but because I'm using 2 different ESPs, I have to define this. That's what that is. Next, we want to expose. So at this point, we have started emulating. Now we want to expose register addresses to the bus. So I define a struct that has it's called a register map, right? So this actually, if you ever use an I2C sensor or device, they always have a register map, as I explained earlier, that stores different values. So you can store data 1, data 2. Data 1 can be temperature, data 2 can be, I don't know, speed of something, depending on the sensor usage, other functions. So I have 3 registers: device ID, data ID, and data 1 and data 2, and I'm calling them register map T. So these are a couple of optimizations that I won't go into at this point. Slave device attributes. So we have an error and then we have a slave handle, right? So we create an I2C device. Basically, this is a configuration struct, right? What are the characteristics of this I2C slave? So we are using the 0 port, or I2C port 0. As I said, ESP has 2 ports, 0 and 1. Clock source is the default clock source. SDA pin is what we have just defined up here, 19 and 18. slave address is 0x48, and buffer depth is just what's the biggest size of our buffers that we need to handle 128 bytes, right? Okay, so this is basically, as it says, emulate some fixed, so it's not random, it's just fixed data. It's arbitrary, they mean the same thing, doesn't matter. Anyway, so these registers, this is me just feeding or forcing data into those registers that we have. This register map right here. In an actual I2C device, this data comes from a physical peripheral. So for example, if your sensor is reading temperature, there will be some physical conversion mechanism that reads temperature from the environment and then maps that temperature to that given register, right? Or in case of our like our MEMS devices, the ones that are used to measure things like inertial movements, accelerations, velocities, etc. This data will come from uh, those physical, I don't remember how they are called, Coriolis something, I don't know. But anyway, that's where that data comes from. But for me, I've fixed it here. Right, so next is we have two things now. Slave tx load. So this function loads requested data into the slave internal transmit buffer, right? So this function slave tx, it takes whatever data has been requested by the master and then puts it into the I2C slave buffer, right? It does not transmit it. It's like a shelf, right? It says take this book and put it on the shelf. The master or the owner will come to pick it. That's the whole point of this function. And you see it's called I2C slave transmit. Again, this is an API function well documented on the ESP-IDF documentation page. We take the slave handle. Now, register pointer starts at 0, which basically means it's this guy here, right? It's at 0 at the start. And this is converting it to just a byte array, right? Because we want to send data on the I2C bus is transmitted as byte arrays. That's the protocol definition, right? So the length is basically how many bytes do we want to transmit from our slave. So go to this slave register address, count the number of registers you want to send, and transmit those, or rather put them into internal TX buffer, right? Counter function to this is a Rx task. This is basically receiving from the master. So this function sets the received master register request, right? So it's a loop because we can receive data at any given time. We don't know when master will try requesting for data. So we have an API function here called I2C slave receive that takes a slave handle, and what are we receiving? It's just basically a byte. So we pass a reference to that byte, and we want to receive only one starting. We want to receive the first byte the master has sent. Then we update our register pointer to be Rx. So whatever we have received, if we send 0x01, for example, our register pointer will be 0x01, which is register 1, which means it is this register right there, right? So this Rx is what we have received from the master. So if the master wants to read data 2, the master will send 0x02. Okay, so that's what we put here, because this reg pointer is global, that's why we are copying at this point. So make receive, let me just comment it, make receive data global. There's no need to comment, but just to explain. And we delay for 5 milliseconds. Ideally, you want like, you don't want to delay it blocking, but you can use whatever value you want. So that's it. So this function receives data from the master. This function sends data to the master. Good. Now the last thing is our main function right here. What does it do? The main function creates these tasks, right? Actually, it creates a slave Rx task, You can see this is where is it? This is a task that runs definitely. Scheduled by the task scheduler from the RTOS. Of course, we have an error checking whether we create a new I2C slave device. Remember the slave device we created with these configurations. This is where we load it into the bus. And then we check now if this device was not created well, we have an error message. Otherwise, we run our super loop. So our super loop runs only one function, which is the slave tx load, right? So it loads what length. So I'm passing 1 here for a fixed. This is basically actually for testing purpose. So you should, or rather I'm loading 1 byte into my transmit buffer, right? So if this receives 1 here, we have the slave handle, that is okay. Register pointer is whatever thing has been received from the master 0x02, right? So master sends 0x02, register pointer is 0x02, which is 2, right? In our super loop, we are running slave tx load with 1 byte. So it means that at this point length is 1, register is 02, which is 2, right? So this is 2, this is 1. It means we transmit 1 byte starting from address 2. So we'll send that. Okay, so that's the whole point about the slave. That's a slave device, and that is what it does. So I'm going to run this. I'm going to run it and show you how it runs. Yeah. Okay. So at this point, the master, where's the master code? Right here. The master is sending 1. Okay. Sending 1, and I want to check the data address that I want to read is 00. Okay, so let's see. So my register here is 00. So I want to read address, another register 0x00 from slave. That is what I'll pass here. So in my slave, what I expect to return is what is held in slave, register address 0, which is the device ID. At my device ID, I've had coded it to be the slave address, which is basically 0x48. So I expect it to return for me 0x48, right? So I'll run that. Let me open the terminal here, and then reset my ESP. Reset. Okay. So ignore all of this other information, and good. So what we have here is received. Let me close it. Received value H. So H is not 0x48, but it is actually 0x48 because what I did was in my master code, I just received this character. I'm printing a character. So it means if I search for ASCII table, ASCII, where is ASCII? I had an ASCII table open somewhere. Yep, I have an ASCII table. Good. So if you look clearly, it is printing a character with a value of 48, with a value of H, right? So what is H in the ASCII ASCII code, right? Let's look for H. H should be 48. I hope it is 48. H is a capital H. Capital H. Where is it? Yeah, it's right here. Good. So if you look, you realize that H is 48 in hexadecimal, which is basically our slave ID, right? So that's perfect. So this works as you would want it to work. If you wanted to print in hex you can write things like 0x, something like that. It'll print for you 48, but doesn't make a big difference. Okay, so that's it. That's how to emulate a very basic, simple master slave device using ESP-IDF. It would be easier if you had all these abstractions done for you with maybe Arduino or Platform IO, but I'd rather go with the most low level stuff. That's why I've gone on through all this trouble of it's not really trouble, but of configuring the master slave bus etc. Right, so that's it. Let me know if you have any other question, and see you next time.